So in this second part of talking about the chemical senses, I'm going to continue talking about taste and the neural code actually for taste, for the research that shows how we know, how we code for taste, and then also talk about individual differences in taste. So as we talk about how we code for taste and taste quality, we're going to end up talking about that controversy that we have seen several times now between distributed coding and specificity coding. And I'm going to start with Robert Erickson's pretty classic now experiment that was done in 1963, where he looked at these across fiber patterns in the chorda tympani. So if you remember, the chorda tympani is one of the cranial nerves taking the information from the taste receptors to the medulla in the hindbrain. And he looked across, so if you look at the figure, the chorda tympani fibers, he gives us fibers A through M. So he's looking at the firing rate of various chorda tympani fibers. And we're going to start by looking at the response of rats and the measurement in these chorda tympani fibers to ammonium chloride, or what you see there at the top in the red line, the NH4Cl, and potassium chloride, which you see in the green line, KCl. So those both taste kind of sour. And what we see is that for rats, the ammonium chloride and potassium chloride have really similar patterns of activation, where A through C, we have the same amount of activation, and then E through M, we have really similar amounts of activation, and the only real difference there is D. But overall, that across fiber pattern looks relatively similar. And then if we look at sodium chloride, which tastes kind of salty, in the open dots, you can see that the across fiber pattern is really very different. A through D look relatively similar. You might even say A through E. But then as you get to F through M, those fibers are responding very differently. Okay, that is the neurological code for these taste qualities. But what about perception? And the question is, does this match perception? If we ask about the perception for rats, what they ended up doing was, let's just say, I'm going to say that we are going to choose ammonium chloride. And in that instance, they're going to taste ammonium chloride in water, and the rats are going to be shocked. Okay, so they are going to learn an aversion to ammonium chloride. And then if we give them a choice between the potassium chloride and the sodium chloride, they avoid the potassium chloride and they still drink the sodium chloride. They have done this vice versa, where, so if I start with the potassium chloride, and what I do is I shock the rats when they're drinking water solution mixed with potassium chloride. Then we try the ammonium chloride and the sodium chloride, and the rats avoid ammonium chloride and drink the water with the sodium chloride. And so in both of these cases, what they're doing is they're avoiding the substance where what we see is a very similar across fiber pattern for those in the brain. They're communicating to the brain in that cranial nerve. For humans, we can just ask them which of these taste similar and which of these taste different. And for people, we agree that ammonium chloride and potassium chloride, they taste kind of similar. And then when we taste the sodium chloride, we say, hey, that tastes really different. And that too matches the across fiber pattern of what we see in the neural code for rats. So this looks like distributed coding, right? Like what we're doing is using many neurons and the pattern of activity across many neurons to code for taste. We are also going to look at a number of studies here that found evidence for specificity coding, particularly early in the taste system. So actually the chorda tympani is very early in the taste system. That that cranial nerve is coming straight from the taste receptors in the tongue to the medulla in the hindbrain. But what Ken Weller and his colleagues looked at was genetic cloning for particular taste receptors. So we have receptors for sweet, bitter, and umami, those protein strings that cross the taste receptor membrane 7 times. What they examined specifically was this PTC, or phenylthiocarbamide. Normal mice do not have that receptor for PTC, or phenylthiocarbamide. From now on, I'm going to start calling that PTC, and I'm going to stick with PTC, as I'm going to use this and talk about this several times. Normal mice do not have that receptor, but then they genetically cloned mice to have the PTC receptor. And so PTC is a particularly bitter taste or smell if we get it up our nose. And if you look at the normal mouse, they mixed PTC with a water mixture, and then the normal mouse would keep drinking the water mixture. What we see in most animals, and mice included, is that we mammals tend to avoid those bitter tastes because, again, typically they mean something's poisonous, something is really bad for us. And so the normal mouse without the PTC receptor is drinking water just the same, regardless of how much PTC is mixed into the water. Whereas when they take a mouse and they genetically clone that mouse to have a PTC receptor, you can see that the more PTC that is mixed in with the water, that we see less and less licking or drinking of the water, as they are not liking that bitter taste and are avoiding it. And so that genetic cloning makes it look like specificity coding, that this is a particular receptor that is responding to this particular bitter taste. But notice both times that I'm saying, like, really this specific receptor and this specific bitter taste. Weller and his colleagues not only looked at the PTC receptor, which is given in A, and that says exactly what I just said with the figure, but they also looked at cyclohexamide. So a normal mouse has cyclohexamide, and a cloned mouse, they genetically clone these mice so that they do not have a cyclohexamide receptor. And again, this is a particular chemical that creates a bitter taste. So the mice with a cyclohexamide receptor will avoid the water mixed with cyclohexamide, and a mouse that is cloned to not have that cyclohexamide receptor does not avoid the water mixed with cyclohexamide. So again, a particular receptor responding to a particular chemical causing a particular taste. This suggests a specificity coding. Another study where they interpreted the data as supporting specificity coding was a study where they used amiloride, and they applied that to the tongue, which the amiloride blocks the flow of sodium to the taste receptors. And we're looking at the response of 2 particular neurons in the rat's brainstem, so in the nucleus of the solitary tract. And if you'll notice the neuron in A, and you can kind of see at the very bottom, he's labeled what these N1, N2, what those tastes are. So those early ones are salty. And if we get to QCLH, we get to the bitter sour area, and then here's the sweet off to the far right. So in A, that neuron is really only responding, so we see the number of spikes per second, or how many impulses per second we're responding at, is really responding the most to salt and not really responding much at all to any other tastes. We see a very small pop up at a sweet taste. Okay, and if they apply amiloride to the tongue, what we see is the pinkish purple line, and now that particular neuron that responds to salt isn't responding to anything anymore. So we see a decrease in the responding of neurons that respond to salt, but not to neurons that are responding to salty and bitter. So if we look in B, this is a different neuron and it's responding to salty and to bitter, and its blue dashed line is what it normally responds to. So we see the pop up at salt and at bitter sour, and at the pinkish purple line after they have applied amiloride to the tongue. That's having no influence on the response of this particular neuron, which suggests, again, this kind of those specific neurons are responding to specific taste qualities, suggesting a specificity coding. And finally, there is a study that looked at 66 different fibers in a monkey's chorda tympani, so in that cranial nerve, and how those different nerve fibers were responding to taste. And if we look at their response to sucrose, we see that there are specific nerve fibers, particularly 1 through 9, 10, around there, that are responding pretty strongly, and then otherwise not so much. If we look at salty, then about neuron 16, 17 through about 30 are responding pretty strongly, and then again we have this pop up at 45, about maybe 45 through 49. If sour, we have neurons 45 through 50 about responding pretty strongly, and then not really much else, although a teeny tiny bit down there at 21. And then at bitter, we have more neurons responding up at the other end, so about 54 through 60, let's say, are responding pretty strongly, as those, again, on the y-axis is the number of spikes per second, or how many impulses per second is the neuron responding at. So usually at this point, I ask, what do these graphs seem to be showing? Again, this was taken as evidence for specificity coding, and he shows us at neuron number 5 that that particular neuron is responding to sucrose, to my sweet taste, and not to sodium chloride, hydrochloric acid, or quinine, not anything to my salty, sour, and bitter tastes. But you can think, does it really look like specificity coding? It certainly does not look particularly distributed, that we're looking at some pattern. But to me, it looks almost a little bit like kind of sparse coding, that there is some overlap, and maybe there is a bit of maybe a pattern. I don't know. It's pretty good evidence for specificity coding, but it's a nice thing it's a good thing to think about, and it's a good thing to think through the argument about what that means, specificity coding versus distributed coding or population coding, to think that through again. At the end of this section of the chapter, Goldstein talks about individual differences in tasting, and I know that most of us find this pretty interesting because we've had friends or family members who really enjoy things that we don't like at all, and then they really dislike things that we enjoy, and we wonder how is that possible? And to some extent, I think a lot of us put a great deal of stock in personal experience and environment influencing our individual differences in tasting, and it does. I mean, we see real cultural differences, which is one example of how acceptable some things are. So eating bugs is acceptable in some cultures, whereas because I grew up in the United States, I feel like that's kind of disgusting, but they think it's not. They're actually really good protein, and I'm sure they taste fine. It's my own kind of mental block that does not allow me to eat bugs because of my culture. But we also we have different personal experiences with taste. We have different conditioning, classical conditioning that's occurred when we are eating certain foods, and it's more complicated than just taste. In that case, we're going to be talking about flavor after we talk about olfaction, because really when we're tasting something or eating something, experiencing the flavor of something that's spicy or has the several aromas and flavors kind of mixed together, and we can smell or taste the lemongrass and the mushroom and the sort of the richness of our foods. That is a much more complex experience, and that does include a lot of influence of olfaction, of our sense of smell. But I think one thing we don't really necessarily know, and that lay people don't necessarily know, is that there are genetic differences in our ability to taste certain substances, and then how strong or weak those different substances are. And it's that we have differences in the number of taste receptors. We have differences in the types of taste receptors that we have on our tongues. And so one of the early studies looking at this was really an unofficial kind of study done by Albert Blakesley in 1934 at the American Association of the Advancement of Science meeting. Before that, so Arthur Fox was pouring this PTC. I've talked about PTC before when I talked about genetic cloning. So phenylthiocarbamide is, for most of us, a bitter substance if we have the taste receptors that respond. And what Blakesley did was just this really unofficial kind of poll of people walking by his station, and he found that 66% found PTC to be bitter, 28% found PTC to be tasteless, and then 6% found PTC to have some other taste. This is usually one of my demonstrations in class, and in every class that I've done this in so far, I find really, really similar proportions. So about 2/3 of the class say that it's bitter. About 1/3 of the class raise their hand when I say who thinks it's tasteless. And then I have just 1 or 2 people here and there to say that it seems to have some other taste to them. So people who taste PTC have now been labeled as they are called tasters, and people who do not taste PTC have been labeled as non-tasters. This is kind of a fun thing to do, although PTC in large amounts is a poison, and so if you go and get the PTC strips, they are not expensive, but don't use a bunch of them. Just you use one, and that's the way that works. But I did do this with my family. My mother does not like those bitter green vegetables, and she does not like dark chocolate. And I'm like, what kind of freak doesn't like dark chocolate? Everybody loves dark chocolate, but it does have this kind of a little bit of a bitter taste to it. And so I assumed that she was a taster and the rest of my family was non-tasters because she tastes bitter more than we do. But it did not work out that way. So again, I think we're gonna, as we keep examining these genetic differences, I think we're gonna keep finding more genetic differences because we do have different kinds of taste receptors on our tongues. But so it could be that she's a super taster and we're just tasters. It could be just those particular bitter compounds. They don't even have PTC, so this isn't exactly, this doesn't line up completely, but I still had this feeling that she was a taster and we were non-tasters, and that was just not the case. One of the pretty well-known researchers in the field of taste is Linda Bartoshuk, and she has looked at genetic differences. One of the things she's done is looked at video microscopy, where she has counted taste buds on people's tongues, and she found that people who could taste this prop, this chemical 6-N-propylthiouracil, they had higher densities of taste buds than those who couldn't taste it. So they had more taste buds in these little areas where they were counting taste buds. And then Delwich et al., 2001, they show that the density of taste buds alone does not explain the differences in sensitivity. And in fact, they stimulated the same number of receptors in tasters and non-tasters, and they found that tasters have specialized receptors that are absent in non-tasters. So we can go back to that example of PTC. It's not just the density of taste buds, but am I able to experience a particular taste, a particular substance? And so they labeled people who are especially sensitive to this prop, to that particular chemical, as super tasters, and say that they may be more sensitive to bitter substances in general, which is why I said now maybe my mom's a super taster. We all appear to be tasters, but it's interesting how we have these individual differences, and those differences in the numbers of taste buds is going to influence how strong or weak a lot of tastes are in general. But we're going to have different types of taste receptors as well. That's going to influence how much we are tasting. Sweet, salty, bitter, sour. And umami and fatty acids. At least those 6 things that we know of.